Welcome to Spring LIB.
Hi, let us consider two wheels of radius 6 inches. On one wheel, we have a point attached to the circumference. Let us call the center of these circles D and E. And then we have a rod AB where A is attached 1 inch away from the circumference. So if this is 6 inches, then the distance between A to D is 5 inches. And point A has a rod with a pin attached to point B here. This radius is also 6 inches, but the distance from B to E is 4 inches. The length of the rod AB is 14 inches. And then we are given that D is moving right with a velocity 6 inches per second. Now, both of these discs are on a surface and they are rolling without slipping. So if you remember our problems from rolling without slipping, that basically means that the point in contact is going to have a net velocity 0. So based on this condition, we are asked velocity of point E. So there are three rigid bodies in the problem: the disk with center D, the disk with center E, and the rod AB. So what we'll do is we'll sequentially find the net velocities of each points, and by net velocity I mean we'll sum the translational plus rotational velocities until we get to point E. So let us try to do this strategy. So what is the velocity of point A first? Let's say so this is point D, this is point A. So translational velocity is same for all the points on the rigid body. So this is going to be 6 inches per second, as this is 6 inches per second. Now, what is the omega, the rotational velocity of this disk? That can be figured out because, as I said, since the translational velocity is the same for all the points, and we know that the net velocity of this point in contact, let's call it C1, let's call it C2. So we know that the rotational velocity at point C1 has to point opposite to this translational velocity, because the net velocity, so I'll just write this rule down, net velocity for C1 and C2, which are points of contact, for rolling without slipping, they have to be 0. Or let me just write it in a slightly more mathematical way. So net velocity for C1 and C2 is 0 for this condition, rolling without slipping. So I should say if rolling without slipping. Right. Okay. So then at C1, we know that this velocity is going to be 6 inches per second. And we know that the radius of the circle is 6 inches and VR is omega cross R. The direction is already determined, so it's just going to be omega times R. And since radius is 6 inches, the angular velocity is going to be 1 radians per second. So let me just write it down in case. So this is going to be 6 inches per second equals omega. Let's call it about D. And then radius is 6 inches. So 6 inches cancel, and omega D is 1 Radians are dimensionless and 1 radians per second. Okay. Now, what will be the rotational velocity at point A? So rotational velocity at point A will point perpendicular to the circle at point A, and the magnitude will be omega d times the distance between A and D. So let's call it RAD. So this will be 5. So this will be 5 inches per second. But we need to find this angle as well, figure out the total vector velocity of point A, right? So what is this angle? So this angle can be figured out with a bit of trigonometry. So we note that this is 14, the length of the rod, and do we know any other information to figure out this angle for now? So if this is the horizontal, then let us continue solving and we'll probably figure out the correct angle for the velocity. I think, yeah, I think I drew the diagram in a slightly confusing manner. The point A is just directly above point D. So let me just correct these diagrams. So it's not explicitly given in the problem. That's the problem. Like you have to figure out from the, like it's not written in the problem, but it's drawn such that point A is directly on top of point D, and then point B is in a horizontal line with point E. So this is the situation, in fact, for the rod. So in that case, we can easily figure out the angles because now it's a right angle triangle and the velocity is actually not going to point at an arbitrary angle like this, but since the point A is directly above the center, the velocity is actually going to point along the horizontal perpendicular to this radius vector dA, and the magnitude will be the same. It will be 1 times 5 inches, so 5 inches per second. So the total velocity, net velocity at point A is going to be 6 plus 5, 11 inches per second. Okay, so now we have figured out the velocity of point A. Now let's try to go to point B. So let us again draw the diagram. So we know the velocity of point A. This is 11 inches per second. Then let us consider this as translational velocity. And then for rotational velocity, since we know that in the net velocity, the velocity of A has to be 11, we can take point A to be fixed for the rotational part and consider a rotation about fixed A. So this is 11 inches per second. This is 11 inches per second. Now what about point B? So at point B, we don't know the velocity yet, but we'll know it when we consider the other circle. So because it is also attached to a circle, a circular disk, so the motion of point B is also going to be restricted. So this is the diagram for AB. We already know the direction of the velocity though, because as I said, it's in a horizontal line. So again, the diagram, they didn't say it explicitly in words, but the diagram shows that B and E are in a line parallel to the ground. So basically along horizontal. So since B is moving in a circle with the center along, with the radius vector along horizontal, the net velocity of point B, since it's attached to a pin, has to come from the rotational velocity of rotational velocity, and there can be a translational motion as well. So we can't really say that it always has to point like this. So okay, so we can only figure it out after we analyze motion of the third disk as well. Okay, so let's leave it like that. Let's go to the second disk. Sorry, third rigid body, second disk. So this is our disk with center E, and so the question asks the velocity of point E anyway. So let us assume that this is some velocity VE. So I drew too long of an arrow. Let me draw a slightly shorter arrow. So this is VE, and then point B is along the horizontal. So, and also it's closer to E because it's only 4 inches away. So this is point B. So translational velocity by definition is going to be same for all the, so let's not call it VE, but let's call it VT of E, which is V translational at point E. So VT of E, VT of E. This is going to be same for all the points, and then plus there will be some rotational velocity. And what will be that rotational velocity? So it has to cancel the velocity of the center E. So it has to point like this, which means the omega will be something like that. And this will give us the net result which we want, where here the velocity of C2, net velocity at point C2 is 0. So, and at point E, since it's at the center, actually the translation velocity is going to be the net velocity because there is no radius. So radial velocity omega cross r is 0. So we can indeed, this translational velocity, we can just denote as VE, which I was doing earlier. So it was correct. But we have to remember that each point of the disk will share the same velocity because that is the definition of rigid body. Okay, so now, so what is the omega for this? So we know that here V rotational has to equal VE. So omega of E times radius, which is 6 inches, has to equal VE. So this is one equation, and then this gives us omega E, which is VE over 6 inches. So we'll not write the units, but we'll remember that, or maybe let's just keep the units. And at point B, the rotational velocity is going to point, because of this direction, it's going to point up. So what is velocity of point B? The vector velocity is going to be sum of translational plus rotational velocities. Translational velocity is just going to be VEI plus rotational velocity is going to be VE over 6 inches times 4 inches, which is because omega E cross R, and this R is 4 inches. This is in direction J. So we can simplify this. This will be 2 over 3. Okay, so now we know the velocity at point B. This is the net velocity. So since we are assuming the motion by keeping A fixed in the rotational motion in this part, we can assume that B also shares this velocity, which is the translational velocity, definition of rigid body, 11 inches per second. And then we can assume some omega here. So since we know that the net velocity of B has both I and J components, so the velocity and I component is bigger than the J component, although that information is not really required. But since you know that the velocity will point something like this, leaning more towards horizontal. And this velocity, this is the net velocity. And the rotational velocity is always perpendicular to the radius vector, so it will always be perpendicular to rod AB. And if we have an omega AB here, then the magnitude will be omega AB times 14 inches. And this will point perpendicular to the rod. So the sum of 11 inches per second and then omega AB times 14 inches should give us a velocity which is net velocity, which is at point B, which we have figured out to be VE in the horizontal direction and 2 by 3 VE in the vertical direction, because this is the velocity VEI and 2 by 3 VEJ. Okay, now what is the angle this rod is making? Because we need that angle to sum these two vectors, the 11 inches per second and omega AB times 14 inches, that part. So to get that angle, let's look at this diagram again. So A to D is 6 inches, and then D we have, then D and E have to be in a straight line, because again this diagram is slightly confusing, but the center line has to just join, because yeah, let me modify this diagram slightly so that this point of confusion is also gone. So we have two discs. Again, this would not be necessary if the problem in the words said clearly that A is on top of D and B is actually in a horizontal line with E. I just drew it like that, but didn't say it in words. But so I just tried to keep it general, because this was not the given information, but you had to infer it. So anyway, so it's E, it's D, then point A is somewhere here, point B is somewhere here. Okay, so then let's draw AB, and this is a rod, but let me just draw a straight line just to keep it neat. And then D and B are in a straight line. So this is A, and AB is 14 and AD is 5. So this is going to be square root of 14 squared minus 5 squared, and 14 squared is I think 196. 14, yeah, 196 minus 25. 196 and minus 25 will be 196 minus 20 is 176, so it's 171. And then square root of 171 is, just quickly calculate that. So 171 to the power 0.5. This is 13.07. So let's just take it to be 13, close to 13, up to one digit of decimal. This is correct. So 13. So then we can figure out what angle this rod is making. So if this rod is making an angle theta, then sine theta is going to be perpendicular over hypotenuse, which will be 5 over 14, and cos theta will be base over hypotenuse, that will be 13 over 14. Okay, so with sine theta and cos theta in our hands, and this angle was theta, so this is perpendicular to it. So, and this is 90, so this has to be 90 minus theta, so this angle has to be theta. So okay, so now we can add these two vectors easily. So we get two equations. 11, so for x component at B, 11 inches per second plus omega AB 14 inches per second, sorry, 14 inches only, not per second, because omega has per second units. Then the angle is 90 minus theta with horizontal, so the horizontal component is going to be sine theta, which is sine theta is 5 over 14. This is equal to the horizontal component of the net velocity at B, VE. Similarly, for vertical component, we have no vertical component for point B, because the translation velocity is purely along horizontal. So it's 0 plus The rotational component is going to be omega AB, and then 14 inches, and then this is cos theta, so 13 by 14. Let me just write it down in case. So this is sine theta, this is cos theta, and then this is going to be 2 by 3 VE. So since we want VE, let us just get omega AB in terms of VE. So omega AB, this 14 cancels. Omega AB is going to be 13 will come down. So 2 by 39 inches VE. And then if we put this back in equation 1, so this is equation 2, this is equation 1. So equation 1 will give us 11 inches per second plus 2 by 39 inches, 14 inches, and then 5 by 14. Actually, we should have cancelled this 14 here itself. So that 14 is cancelled. So we just have 5 inches equals VE. And then here also we had a VE. Okay. So this is 10 over 39. This will go on the other side and subtract. So 1 VE minus 10 over 39 VE is going to be 29 VE over 39. And then inches have cancelled. So this is equals 11 inches per second. So VE is 39 times 11 inches per second divided by 29. So we can calculate this number. So we put them in the calculator. Actually, I can approximate easily by considering 39 to be 40 and 29 to be 30. So let us just write it down. This number is 29 times 11 divided by 39. So this is 8.179, which is 8.18. Oh, sorry, it was 39 times 11 by 29. Okay, I calculated the opposite number. Okay, let me just quickly correct that. So this is 39 and this is 29. Okay, 14.793. So it's close to 14.8 inches per second. So this is how you can solve for velocity of a series of rigid bodies if you just follow each point one by one and draw the diagrams where you follow the rule translation plus rotation equals net velocity, and then just equate the corresponding components. In fact, this has been the principle throughout this chapter. So you follow this and you will be able to solve any of these problems. See you in the next problem. Bye.